All right, so I want to continue our discussion of Carl Lagrangians. And what we've done so far in lecture is we've talked a lot about how to deal with Carl Lagrangians from a top-down procedure, where we have a Lagrangian which had some massive fields as well as some massless Goldstone bosons. We integrated out the massive fields explicitly to construct the Carl Lagrangian. And when we did that, we also saw that there was different ways of representing the fields. So we could have an exponential representation or a square root representation of the fields, or a linear representation. And we saw that there was advantages to some representations over other representations, in particular for nonlinear realizations of the symmetry, nonlinear representations of the fields. There was an automatic derivative coupling of the fields in the Carl Lagrangian. That was very useful for carrying out calculations. So what I'd like to talk about now is in more detail, a different approach. Let's imagine that we don't have this theory that we can integrate out fields from, but we want to construct the Carl Lagrangian from the bottom up. And I mentioned a little bit about that already in lecture, but really what I'd like to do here is go into much more detail on a procedure called the Ccw procedure. And this is a procedure for constructing a Carl Lagrangian given just a minimal amount of information. We have a group G. Its symmetry is broken down to a subgroup H, and that's all the information we have. So how do we construct a Carl Lagrangian for the Goldstone bosons of this symmetry breaking, given that limited amount of information? And so let's review a few different things. So we know that the vacuum manifold is G over H, the coset. So this is the vacuum manifold. And just to have a picture of what that looks like, let's imagine that it's some curved manifold. I'll just draw the curved manifold as a sphere. And so this is the space of possible vacua, or the points on this sphere. And to set up perturbation theory, we have to pick some special point, which is the point we're going to do the perturbation theory around. So let's just pick the north pole of the sphere. I'll call that O, the origin. And we're going to do our perturbation theory around that point. And the Goldstone bosons are fluctuations about that point, massless fluctuations. And so essentially what we've learned is that it's nice to set up the Goldstone bosons as fluctuations about this point, where we capture also the curvature of the manifold. So there's some fields that are the fluctuations, and these are our Goldstone fields. And when we deal with nonlinear realizations, what we're doing is we're taking into account the curvature here of the manifold when we construct our fields for the action here. So we want to set up in general, though, if we just know that we have this symmetry being broken, we'd like to have an idea of how to set up those fields. What are the right variables to use? OK, so we want to describe fluctuations about the origin. And what fields do we want to use to do that? And so this procedure by Callan, Coleman, West, and Zimino, or that's the CCWZ, is a general procedure for doing that. And what it says is that, well, it's going to be some group element, which I'll call Cascade. So Cascade is an element of G. And it's going to depend on space-time, because we're interested in describing the local fluctuations, how the condensate that's described by these Goldstone bosons, how it changes as a function of space-time. And what the CCWZ procedure is it just says, well, let's take an exponential representation for this. So we write it as an exponential. And in this exponential, we have some choices to make. We have to make one choice for some broken generators. These are the x's. We have our Goldstone boson fields, the pi a. And then there's also some normalization. Since the exponential should be dimensionless, we have to pick some norm, and that's what this tau is in the denominator. And so, but we're just going to pick this exponential representation and use that to parameterize the G over H vacuum manifold. And so in general, what we're saying is if we have some element G, little g that's in G, we can always write little g as something in the coset, which is something that has the group structure of this cascade, times a little h, where little h is in this group H. So little h is in big H. And so that's always one way of parameterizing any element of the group. And we're going to do that for the local field construction, where we use this exponential representation. Okay, so that's the idea of the CCWZ parameterization. It's just to pick this parameterization. And so the question that we have to address is, how does this guy transform? Because really all we know with this symmetry breaking structure, really all we know is the transformation properties. That's what we're going to use to construct our Lagrangian. So we really care about how does this cascade field transform. Okay, so let's answer that question. Well, in general, if we pick some element little g of the group, then the cascade's an element of the group too. So group transformation is pretty simple. We simply have multiplication. So here's the result of doing the transformation. And if we just stop there, then that would not really be good, because this would not in general be an element of the form where we have cascade times h. In fact, it's in the opposite order. So what we want to do is we want to write this back in a canonical form. So we can call this structure here the canonical form. And we always want to write everything back in terms of this canonical form. And so if I take my transformation, I can always do that and write it back in terms of the canonical form. This is now in canonical form. And that is how we figure out how the cascade field transforms. It goes from itself to g times this, but we can always write that in terms of this cascade prime. And so the bottom line is that we have the following transformation law for the cascade field. We start with cascade, and it gets transformed to cascade prime. And cascade prime, by this formula, is just equal to g times cascade times h inverse. So let me put a box around that important formula. And in general, in order for this to work, it's not enough that we just have a universal h that's independent of space-time. We actually are going to need an h that also depends on space-time. So h here, in general, will be a function of the group element g as well as the cascade field. OK, so that's the general CCWZ construction. We use this exponential representation, and we have this transformation law here. OK. So I'd like to do a couple of examples of this. So let's, in particular, focus on one example, which is an important example in QCD, which is the following. So QCD has a group SU2 left cross SU2 right, which is broken down to the subgroup, which is the vector diagonal subgroup. And this is the chiral symmetry of QCD for light quarks, the up and down quark. And so I'd like to use this as my example. This is my G, this is my H, of this formalism that we have over here. OK, so let's set up some notation. In order to describe this product group, let me say that my group element G is just a little matrix that looks like this, where capital L is a generator of the SU2 left, capital R is a generator of the SU2 right. And then for this vector subgroup, I'll just say that I have an H, which looks like this. So the product structure is the fact that the off-diagonals are 0. OK, so I'd like to describe this under this formalism. And we have to go back and address some of the choices that we had when we were setting up this formalism. So one of the choices that we had is this X. OK, we said it's the broken generators, but what are the broken generators? It's obvious what the unbroken generators are, because we have a group there. But what are the broken generators? Well, there's some number of generators that we had here that we don't have here, but which ones? We have a freedom to pick which ones. And so we're going to discuss two different choices. So let me start with the first one. So we'll just pick two different choices and see how things work out. So choice number one, let's just take the x's equal to the taus, which are the left-handed taus. So these are the generators of the SU2 left. And that's just some choice. We can make that choice. And then let's see, with that choice, how our formalism here works out. Well, OK, so what is this cascade field with that choice? Well, the cascade field is an exponential. So it's e to the I tau left pi over our other tau. And so since this is, we can write this in this matrix notation. So this is an exponential, an I, and we only have an entry in the left-handed. So this is just tau by t. And then here we just have 0 by choice. So this is something that I can exponentiate. It's a simple matrix. So if I actually work out the exponential, this is going to be some field sigma of x that sits in the upper left corner. And then I get 1 in the lower right corner, because the e to the 0 is 1. So what we've done here is we've got a sigma field. And that sigma field is simply e to the I tau left, or tau. Try to improve that. Over v. And this is what parameterizes the coset. OK? So that's what this choice leads to. And then we have to answer this second question of how does it transform? So let's ask that. OK, well, we have a general rule here in the box, and so we just have to apply it. All right, so let's do that. So we have Cascade goes to, well, let's just plug in. We have a Cascade goes to G Cascade H inverse. So let's just plug in now what we have. So we have sigma 0, 0, 1 goes to an element of the group. So let's just pick a general element. And then we get Cascade back. And then H inverse. And let me write H inverse in the following way. U inverse, 0, U inverse. That's just some element of H. OK, for reasons that will become clear, I've just chosen this U inverse to be there. And if I'm transforming the 1, so this is a simple diagonal matrix, so I could really think of it as just 2 transformation laws, one for the upper left corner, one for the lower right corner. If I'm transforming 1, I actually don't want 1 to transform. And so the fact that 1 is equal to r times 1 times U inverse, and I want that not to have any non-trivial structure, tells me that I should pick this U inverse to be equal to the r. Or pick U inverse times r to be 1, so therefore that U is just r. That's why I chose it to have this structure with the U inverse. OK? So U is just equal to r. Remember I said that H should just be a function of the group and the cascade, so I'm just telling you now what the choice of that function is, working it out. So U is just simply r here. And once I know that, then I can find the transformation law for the sigma field. So I find that sigma goes to L, sigma back again, and then R inverse, which because we're talking about unitary groups, is just R dagger. OK, so this is the final result in this choice 1. We have this sigma field. It's given by this exponential form, and it has this transformation law. And you may actually remember that that's the same transformation law we found when we were talking about the top-down approach, and we were dealing with the exponential representation. OK, so this is the procedure here, the CCWZ, where we say the same thing coming out, but from a bottom-up perspective. OK, so we've seen one example, this choice 1. Let's see a second example to see what is different if we make a different choice. So let's discuss choice 2. All right, so instead of taking x just to be the tau left, you might say, well, why tau left? Why not tau right? So I could pick x to be the tau right, but then it would end up being really just a mirror of what we saw over here. So let's pick something that's a little more interesting. Let's take tau left minus tau right. Of course, tau left plus tau right would be the unbroken generators, so that we don't want to pick. But tau left minus tau right is a sort of democratic choice. It involves both the left and the right. And so let's work out how the formalism works out in this case. So again, we ask, what is our cascade field? Well, it's just e to the ix tau over curly tau. So it's the exponential of this. And now we have terms in both diagonal entries. And still zeros on the off diagonal. So our matrix looks like that. And again, this just gives some field, which I'll call Ccw. And over here, because of the minus sign, this is actually Ccw dagger. Okay, so now we've picked a representation of the cascade field that looks like that. And again, the key thing to ask, given this representation, so now we have a representation of the coset, which actually looks like it has a very similar form to what we had before. It's just an exponential of tau, the generator's tau, over the normalization curly tau. And you might say it's exactly the same. It's exactly the same formula, but you should be a little bit careful because the normalization here, this tau, doesn't have to be the same in the two cases. So let me call it actually tau prime, just to denote the fact that the normalization doesn't have to be the same. OK, so this is the representation. And the key question, though, is even though it has the same formula, how does it transform? Because it's not necessarily, given that this was different, the same as what we had before. So let's answer that. How does this transform? And we still have our handy transformation law down here on the bottom. And so let's just apply this and see what we get. OK, so we have a cascade, which is a C and a C dagger. And it's going to transform according to this. So again, we have L0, 0R, cascade back. And then we have an H inverse, which again I'll write U inverse, 0, U inverse. And so again, we have two rules coming from this, the upper left corner and the bottom right corner. And so if we look at what it says about C, it says that C of x, if we look at the upper, first of all, it goes to L, C back again, and then this U inverse. And if I look at the bottom, well, that's a transformation law for C dagger. But I could take the dagger of that transformation law. So this would just simply be the product, right? C dagger is R, C dagger U inverse. If I take the dagger, I reverse the order of everything. And so I find that I have U, C, and then R dagger. And in this case, the U actually is a function of space-time, unlike the previous case. And the definition of the U is implicit. It's the solution of this equation. So the solution of that equality gives U. So U is the matrix that's defined such that this equation is true. So this is the transformation law of C, which is obviously different than the transformation law of our sigma over there. Okay, so C is a different field than the sigma, but it's an equally good field. It's simply another choice, and we could set up our field theory in terms of this sigma just as well as we could set it up in terms of this C, and just as well as we could set it up in terms of the sigma. And in fact, if you think about it for a minute, you realize that actually there's a nice relation in between these two fields. We can pick the normalization, or the normalizations, so that we simply have sigma equal to C squared. Okay? And why is that? Well, if we look at the transformation law, if I have C squared, that's this times this. And if I take this times this, the U inverse will cancel the U, and I'll just be left with L and R dagger on the outside. And that's exactly the transformation law for the sigma. So C squared has the right transformation law to be a sigma. And furthermore, the normalizations, this curly tau prime and this curly tau, those were just something that I could choose. So I could always pick the norms so that this formula is true. In particular, I could pick tau prime equal to twice tau, and then I would have this formula be true. Okay, so if you like, we had two different choices. They led to two different fields, and there's a simple relation between them. Both of them are equally good choices for constructing the chiral perturbation theory, and we can choose which one we want to work with. People usually work in terms of the sigma because it has a slightly simpler transformation law than the C. But there's other applications which we'll see later in the course where the C actually is important. And so I'll leave that discussion for later on.